I read through the comments on some of my videos, and a frequent comment that I see asks about the fancy math symbols that we use a lot. These symbols come from set theory. That's where you learn it if you go on to take, set theory or fundamentals of proofwriting or whatever the college class is. And when you take that class, that's kind of where math changes, because before that, at least in the United States, most of the math problems we do are computational. And then once you take set theory, then it's all proofwriting, especially if you're in pure mathematics. So I thought I would take, just some time to talk about some of the symbols that we use so that when you see them, you know how to read the statement that's written down. Because it is kind of like alien language when you see it for the first time. And I like to think of it as like, it looks complicated when you see it for the first time, but really it takes what would normally be really, really complicated, right? And kind of boils it down to like 500 words. Like the English dictionary, I don't know how many words are in there, but it's a lot. But then mathematics is like, okay, we gotta boil it down to like 500 or so words. I actually don't know how many words are there. It's just, well, whatever, who cares? How to read math. So these are some symbols that are the most frequently used, I think. These are the ones that came off the top of my head. So if you see, I guess the caret symbol, we'll call it, that's usually represents and if you flip it upside down to get the V, you get or. So if I wanted to say steak and potatoes, I'd write steak, this symbol, and potatoes. And if I wanted steak or potatoes, I would just put that in its stead. These two symbols, I don't really use these two as much as I used to. And when I took set theory, or math proofs, whatever you want to call it, we used these a lot. But, since moving on to, measure theory, probability theory, all that stuff, we kind of don't really bother with these symbols, because the only reason you really want to use them is because it's, they're simpler than writing out the big long word. But and or are already pretty short, so no one really cares. They just write them out. So this symbol, I don't know how to describe it. I guess an L that's been tipped over usually means not. So if you want to negate a statement like it's snowing outside, you would put this in front of it, and then it would read it's not snowing outside. That's all it really means. And then the triangle means the exclusive or. So this or is different from this or because how would we normally write it is this is the exclusive or and this is the inclusive or. So the inclusive or means that one or the other, but you could also be both. So when I say steak or potatoes, that could be just the steak, just the potatoes, but you could also have both of them at the same time. The exclusive or says one or the other, but not both. It's also like the either or statement if you want to read it that way. So we would say either steak or potatoes in that case. So the fancy little e means is an element of, which comes in place when we talk about some set. You'll see here in a few minutes that I use this symbol. You can see but all it really means is that here is something and it's a part of something bigger. That's kind of what just as an element of means. Upside down A. So these are the interesting ones when you're writing up statements. Upside down A means for every, and backwards E means there exists. So for every usually means that, okay, so out of all the cows in the field, we would say for every cow in the field, if maybe like some of them are a different color than the others, we would say there exists one that is brown, or so for every cow in the field, there exists one that's brown, or whatever. And if you flip these two, it can change the validity of the statement. Like there exists a cow such that for every blah, 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 something magical happens. I don't know. I'm not really good at coming up with examples on the fly, which is why I'm starting to write my own scripts more or less. So we'll get to that when we get there. 3 dots means therefore, usually means that the proof is about to end, and you want to say, therefore, we can prove that pigs fly when the struggling grad student gets 1 million subscribers. Then the arrow means implies, so we have some statement here, and then from that, another statement will follow. A common example that I learned, this is like the very first statement that was used to help teach me, all this stuff, because this was all very foreign to me, would be something like, if it is snowing outside, then it is cold. So we need the condition that it's snowing implies it's cold. And just because you have one direction doesn't mean you have the other direction. So, for example, that same statement would be, if it is cold outside, then it is snowing, which isn't true. Because it can be cold outside and not be snowing. That's typical. But if it is snowing outside, then you know it's going to be cold, because it never snows when it's hot outside. That's the example that we used. But if you have both directions, then you have the double arrow. And the double arrow is usually written with, if, to quote one of my instructors, which just is a short way of writing if and only if. You see it in books a lot too. This book I have here by Gerald Edgar. If you're interested, I recommend this book, Gerald Edgar's Measure Topology and Fractal Geometry. It's a very short book. It's not very long. And he talks about this stuff. He's a pretty good author. I like him. I want to get through the book soon because I want to return it to the library, but just the way he writes it's not super formal. I mean, it is, but it ain't like that Zygmunt and Whedon book that I have. If you want to do some light math reading. And then we have the colon, which means such that. I've seen different symbols for such that, but I like the colon. The straight up and down bar is also used a lot, but I prefer colon. But anyway, those are like the main stars of set theory. If you know these guys, you can, get most of it. And if there's anything that's... Well, okay, I guess I skipped union and intersection, didn't I? But I guess that'll be a topic for another video. Okay, so I had this example here, but I think I'm going to scrap it. I'm going to do a different one. Because one of my favorite topics to learn about in real analysis is the very first topic. And it's always about metric spaces and topology. So the book that I got a lot of this information from is this Kolmogorov book, Kolmogorov and Fomin. This is kind of a pretty popular textbook. I don't know how popular this book is relative to, I don't know what I'm trying to say. It's a popular book. I see it on the internet a lot. I actually had a copy and lost it and had to buy another one. But I just like the way that this book is written. His measure theory stuff I kind of jump ship on. I prefer other textbooks to how he presents it. But the first 6 chapters or so in this book I like. So if you want a good analysis book, Intro to Analysis, I recommend this one. It's, I guess it's old Soviet written style. But if you're an American, you can still read it. I mean, I liked it. Okay, so let's look at an example here. We have some set X. It's non-empty, because if it's empty, it's not interesting. We're going to let it be some set. We're going to define a function on the Cartesian product of x cross x, which means that we take a point from x and we take another point from x. So D acts on ordered pairs from x cross x. And the output of the function D is non-negative, so we don't want any negative outputs here. We call such a function a metric on x if the 3 conditions are satisfied. So this is a definition. I write example here because it's really just an example of how our set notation, or not set notation, but these math symbols are used. So what are the 3 conditions? The first condition says that the distance between 2 points in x, which we will call x and y, the distance between them is 0 if and only if x is equal to y, which means that they're the same point. They may not be numbers in this case, but we say that the 2 elements are the same. We write the equal sign. It's kind of understood that way. So what I'm saying here is that if the distance between the 2 points is 0, then they're the same point. But it also goes in the other direction. If I take a point and another point, then the distance between the two better be 0. And it sounds intuitively obvious, but this metric here, this d function, might be kind of weird. So to put it in layman terms, we'll say something like the distance between New York City and New York City better be 0. However you want to measure distance, the distance from a city to itself better be 0 every time. So that's the first claim. The second claim says that the distance between x and y is equal to the distance between y and x, which means that if I drive from New York to Boston, it better be the same distance going in the reverse direction if I go from Boston to New York. Something like that. Property 2 is called the symmetric property, typically in textbooks. And then the third property says that the distance between x and y must be less than or equal to the distance between x and z plus the distance between z and y. So again, in layman's terms, we would say the distance between New York and Boston is less than or equal to the distance from New York to, what's another city? I guess Hartford, plus the distance from Hartford to Boston. Property 3 is the triangle inequality, and a lot of the times when you're trying to show, I won't say every time, but a lot of the times, the third property is the hardest one to check. So a lot of the times in homework, if you're taking metric space or whatever the class is, I would say real analysis or maybe topology, they'll ask you to verify something is a metric space, and all you have to do is check these 3 properties. And more often than not, property 1 and 2 will be easy, and then property 3 is the one that requires a little bit of work. Seems to be the case a lot of the time. Okay, so suppose that we have this metric space. We can talk about sequences in the metric space, which means that we pick xn to be an element of x. So here's the case, from earlier. Xn is an x for every natural number n. We say that xn converges to x if the following statement holds. So this is an example of our fancy pants math notation. So how I would read this. You read from left to right as always. For every epsilon greater than 0, there exists a natural number n, big N, such that for all little n bigger than or equal to big N, this implies that the distance between xn and x is less than epsilon. So the way I think about this, you can picture something in your head. So you have this sequence, right? You have x1, x2, x3, x4, so on and so forth. What it's saying is that suppose you have, I don't want to waste too much time here, but let's say here's x, right? Here's x. What it's saying here is that for any epsilon, your sequence will be trapped inside this epsilon sphere, if you want to call it that. So here's my epsilon sphere. Radius epsilon. Okay? So x1 might be here, x2 might be here, x3, so on and so forth. But what this is saying is that at some point in the sequence, which is what this big N is, at some point in the sequence, you will be inside this epsilon sphere. And once you're inside this epsilon sphere, this statement that shows up here says that you never leave. So it looks like this. I'm never allowed to leave the sphere. And this has to be true for every epsilon, which is the convergence part, because you can take a sequence of epsilons, if you want, that get smaller and smaller and smaller. So if it gets smaller and smaller and smaller, maybe I'm like this small. You know what I mean? And then you would have to choose a different big N, so that because maybe this big N doesn't work, so then you have to go further along in the sequence until eventually you get trapped inside this ball and you can never leave. And you just make the ball infinitesimally small. So that's where the notion of convergence comes from. Okay, so now let's look at this definition. Koshi sequences. So now we take a sequence, just like we did up here, but we call the sequence Koshi if the following statement here holds. So this is the definition of Koshi sequence. For any epsilon positive, there exists a big N, such that for every m and n bigger than or equal to n, and here it doesn't matter which one you call larger. For this case, I said big N, or excuse me, m is larger than n. If this is the case, then the distance between xm and xn is less than epsilon. And so if you think about this, you might be confused as to how it's different from convergence. In this case, we're not talking about this x here. There's no mention of any x here. Really, what I think of when I was learning Koshi sequences the first time is I just imagined a sequence whose terms got closer and closer together. That's it. We're not saying anything about convergence here. We're just saying that as you move along in the sequence, the terms get closer and closer together. Think, for example, of 1 divided by n. Let xn here be 1 divided by n. And those fractions get closer and closer together. So, for example, 1/2 and 1/3 are kind of close together. But the farther you go, like 1/10 versus 1/11, those two fractions are a lot closer than 1/2 and 1/3. And it just keeps getting, closer and closer and closer together. So you have this notion of Koshi sequences. Some textbooks, by the way, call it a fundamental sequence, which is what this Kolmogorov book does. But he also mentions Koshi sequence. He mentions them both in here. So why do we care about these two definitions? Well, it kind of plays into this notion of completeness when it comes to metric spaces. So we say that a metric space is complete if, given any Koshi sequence, you can find a point in the metric space such that that sequence converges to X. Okay, so in this definition here of Koshi sequence, there was never any mention about an X, like this sequence had to converge to anything. It made no mention of it at all. In fact, given the metric space, there's a whole reason this definition of completeness comes into play, because you can have a Koshi sequence, but it may not converge. However, if you have a convergent sequence, then you know immediately that it is Koshi, and that's usually a popular homework problem that they give you. It's a pretty quick homework problem if you know how to do it. I might do it, in a future video, but not in this one. This video is going much longer than I thought it was going to go. But if you have the other direction, meaning given Koshi sequence, then it converges, then you know the metric space is complete. So I'll give an example here. So suppose that your metric space is the set of all rational numbers, and the distance between 2 points from Q is the normal Euclidean distance. So it's just take one number, subtract the other, take absolute value. That's all you have. So it's very familiar metric space. And then you take the sequence given here. So you let x1 be 1, x2 be 1.4, x3 be 1.41, x4 is 1.414, and if you recognize the pattern here, x5 would be 1.4142, and blah, 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 blah. And you can show via exercise that this sequence is a Koshi sequence. You can kind of just look at it and see that it has to be a Koshi sequence, but you have to do it formally. So notice that each of these x's are rational numbers because they're terminating decimal expansions. 1 is definitely rational. 1.4 is just 14 divided by 10. 1.41 is just 141 divided by 100, and so on and so forth. So all of these are rational numbers. But the way I've constructed this, I'm forcing this to converge to the square root of 2. I'm cheating here a little bit because I don't really know that this number is irrational that I'm constructing. You would have to prove the square root of 2 is irrational, but that's, a common exercise. It's not too hard to do. But I do need to kind of build the sequence in a more rigorous way than what I'm presenting here. But for the purpose of this video, to just exercise set notation, I don't think it's completely inappropriate. But what I've done here is that I've constructed a sequence of rational numbers. It is a Koshi sequence, and it does converge to the square root of 2. But the square root of 2 is not a rational number. So it is a Koshi sequence, but it is not convergent in the space of rational numbers. So, to remedy this, they make the real numbers. So what are the real numbers? You can think of the real numbers. You know, when you're learning this stuff in the 8th grade, they usually just kind of say, okay, you have these things called rational numbers, and anything that's not rational, we call that irrational, and then the real numbers is just the union of the two. You know, that's kind of the very sloppy definition of real numbers. But if you want a more rigorous definition of real numbers, we can say it as the completion of this space here, this metric space. So a completion just means it's the smallest complete metric space. Hold on, I'm going to butcher this definition. It is the... Well, I kind of like to think of it as the closure of the rational numbers. But the completion is just... you know what? I have the book here. Let me make sure I don't stick my foot in my mouth. It's like the smallest complete set that contains the original set. Something like that. Completion. There's a famous theorem called the completion theorem, which takes like 3 pages to prove. The statement is simple, though. Okay, so here's the statement. Given a metric space and with closure, a complete metric space is called a completion of X if X is a subset of X star and the closure of X equals the set itself. In other words, in this case, Q is a subset of R everywhere dense in R star. Okay, so I guess let's think of it as the closure of Q for the purpose of this example. Closure being the smallest closed set containing Q in this case. So that would be its completion. However, this completion property is dependent upon the metric that's used. So yes, the real numbers are complete with this metric. If you change the metric, then you can make the metric space incomplete. So if you let X be the real numbers and you define this funky distance as the absolute value of arctangent X minus arctangent Y, then this metric space is not complete. And the way you can prove that is just find a Koshi sequence that does not converge in the set of real numbers. So this was an exercise from the textbook that I thought was kind of cute. And the way I do it, or at least try and visualize it, is that I draw the graph of arctangent. And if I want to measure the distance between two real numbers, I would say, like, okay, here you have X, and here you have Y, and you go up to the graph. Here's my point. Go up to the graph. Here's my point. And then I look at their usual Euclidean distance on the Y-axis. So the Euclidean distance between X and Y would just be the absolute value of this distance here, you know, just Y minus X. But if I use this metric, then all I do is I pass through this function first, and then I measure the Euclidean distance here. So you can see under this metric, X and Y are much closer. And you can construct a sequence that's Koshi with this distance here, but does not converge. In fact, I think if you just pick an increasing sequence like n, I think maybe n would work. Just do the sequence of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so on and so forth. I think it will tend to pi over 2, but it won't actually get there. And it increases without bound. It doesn't converge in R, obviously, because it increases without bound, but it would be a Koshi sequence because they keep getting closer and closer together. You have to work out the details. It's been a minute since I went through my topology and whatnot, or metric spaces. I don't know what you want to call it. Anyway, I thought this was interesting, so I wanted to make a video on it. Hope you enjoyed it, and I didn't drone on for too long.